Okay, so 9.5, effect of ferrous core in solenoid. So we heard before, the presence of ferrous core, that means the soft iron core, will make the electromagnet stronger. Okay, now let's see the information here. First point, the strength of the generated magnetic field can be increased by about 1000 times by adding a ferrous or iron core inside the solenoid. So you can see by using a soft iron core, it increased by so many times, 1000 times. Okay. Two possible reasons to explain this effect. First, ferrous material has a high permeability than air, stronger ability to support the formation of a magnetic field within itself. So that's the first reason. So basically it means with the soft iron core inside, the permeability is higher. It means it is easier to form magnetic field because of the iron. It is easier to form magnetic field. Second reasons, so you see this point, okay? Ferrous material are magnetic and become magnetized when placed into the solenoid, thus contributing to overall magnetic field strength of the solenoid. So this is the second reason. The second reason is because if you use soft iron core, the soft iron itself become a magnet as well. So it make the overall magnetic field strength stronger because the soft iron core become a magnet too. Okay. Now 9.6, force on a current carrying conductor. So this is what we discussed at the beginning of our lessons. That time I said when you have a permanent magnet plus current, then it creates force. And at this point onwards, we will use Fleming left hand rule. Fleming left hand rule. When you have B plus I become F. Okay. Just now, before 9.6, we use right hand grip rule. So when we should use right hand grip rule, we use right hand grip rule for straight conductor which carrying current to find the magnetic field. Okay, so maybe I put it in this way. Right hand grip rule is used to find uh, the direction of B when the I is at a particular direction. Okay, so it's I and B. So when you know the current, then you can use right hand grip rule to find the direction of the magnetic field. So that is right hand grip rule. For straight conductor, for circular coil, and as well as solenoid, we use right hand grip rule. So with the same purpose, we want to know the direction of the magnetic field when the current flow in a particular way. So that is right hand grip rule. But 9.6 onwards, the situation is more complicated. We have magnetic field, we have current that interact and they produce force on the conductor. And to find out the direction of the force, we use Fleming left hand rule. Okay, so let's look at Fleming left hand rule now. So our hands have to put in a way which is something like a gun, and it will help us to remember. FBI is, the police, international police. So FBI. So F represent force, B represent magnetic field. Magnetic field is north point to south, north point to south. Okay, so current flow in this way. So we have to put in this particular way so that the force, the B and the I, three of them are perpendicular to each other. Okay, perpendicular to each other. Okay, now let's see example. Yeah. Force acting on a current carrying conductor in a magnetic field. Okay, so first of all, I put a dot in the middle here. This dot, right, I had to put it in this way. So this dot is actually a cross, which means the current is going into the screen. It's going into the screen. So you have to use Fleming left-hand rule. Fleming left-hand rule. So what happened is your index finger, this one, your index finger have to point downward. Okay, have to point downwards, and then your current have to point into the screen. Then you will realize that the force is to the left. So you have to try it out with Fleming left-hand rule, where the the B is pointing down, the I is pointing in 90 degree, and then you will realize the force is to the left. They are perpendicular to each other. Okay, so as you can see, I can put perpendicular here and there. So by using Fleming left-hand rule, we will know that the force is to the left. Who get the force? Actually, the conductor get the force. So the conductor will move to the left. Yeah. So use Fleming left-hand rule to determine. And then you see the way that they draw the magnetic field, right? Okay. So if the force is to the left, so the other sides of the conductor, you put more lines. Then this side you put less number of lines. And this kind of magnetic field is called catapult field. Okay. Catapult field. So where the magnetic field is unbalanced, and hence it produces force. Okay. So it is due to the interaction of the magnetic field from the permanent magnet and the magnetic field of the conductor. So that two magnetic field interact and produce this catapult field, and hence there is a force. Okay. So it is the interaction because of the two magnetic fields. Now let's move on. Strength of force can be increased by increasing the current. So logically that is true. If the conductor has a stronger current, of course the force should be stronger. Using a stronger magnet, logically this is true also, because if this permanent magnet is stronger, then the force should be greater also. Okay, so and then it's not just these two. That's for your information. It's not just these two. We have other factors that affect the strength. So current, stronger magnet. So this is actually the I. This is actually the B. So we have the length. Okay, I add it here. The length the length of conductor in the field, and then the angle the conductor make with the field. Okay, so this is the L and this is the theta. So there are 4 factors actually. These 4 factors will affect the strength of force. How to remember the 4 of these factors? Of course, we will learn that very soon, which is here. So you can just look at it for temporarily. The formula is here. The magnitude of the force is calculated by using BIL sine theta. So you have B, you have I, you have L, you have theta. So all these affect the force, the strength of the force. Okay, so we have to understand L and theta first. I and B I already explained. So current and the strength of the magnet, you already know. So L, the length of conductor in the field. So how? Okay, let's say example. I put it at the side here, a drawing. So let's say this is your permanent magnet, north and south. So the magnetic field, like this. And then you have a conductor. Let's say the conductor I put in blue. Conductor, okay, let's say it's like this. A straight conductor. And let's say the current is this way. The current is flowing in that way. So what is meant by the length of the conductor? It is from this point to this point. And this is the length. The length of the conductor is in that way. And what is the angle the conductor make with the field? The angle is in this way. It make with the field. The field is the arrow, no? The arrow, the line with arrow, and then the angle between the red color lines. This is the field and the conductor. So the angle is theta. So then it will affect how it will affect based on this formula. Okay, so there are altogether 4 factors. Okay, now let's move on. Let's look at the next subtopic. Okay, here, forces between currents. Okay, first, let's look at the example here. If you see a dot, that means the current is coming out. The current is coming out. If you see a cross, that means the current is going in. Okay, so the current is coming out for this, and the magnetic field is like that. It's anti-clockwise. How we know? Use right hand grip rule. Okay, the thumb have to point out of the screen. Then the 4 fingers you twist in the way that is anti-clockwise direction. And this one, the thumb, right hand grip rule again. The thumb have to point into the screen. Then the other 4 fingers will twist in a way that is clockwise direction. So that's why this is clockwise direction. Okay. Now at the end, these 2 straight conductors which have current that flow in opposite direction, at the end they will repel from each other. Okay. So if the current flow in the same direction, as in here, two of these are dot, meaning that two of these having current that come out from the screen. Then you use right hand grip rule to determine the magnetic field. Okay, here also they are just anti-clockwise, and at the end you will realize they attract. Yeah, they attract. Okay, so this one, both of these are cross, and then you use right hand grip rule to determine the directions. So where your thumb had to point into the screen. So the direction of the magnetic field is clockwise for both cases. So in this case, attraction again. Attraction. So what we can see here is if the two straight conductors are flow in opposite directions, then it will be repulsion. Repulsion. If the two straight conductors are flowing in the same direction, then it experiences attractions. So that is what we see so far based on the picture. Okay, so let's put a conclusion first. I in opposite direction, then repel. Okay, then this part, I in same direction, attract. Okay, now let's see more information based on the note. Can be worked out by considering one wire's magnetic field using right hand grip rule, drawing a tangent at the position of the other wire, and then applying Fleming left hand rule. Okay, let's see example. Okay, example, I will use this as my example, the first scenario here. So what are they talking about? Fleming left hand rule, right hand grip rule. Okay, so let's say I put a dot, which is this point. I pull it here, a dot. Okay, so a dot is there. Then that means the current is coming out from the screen. Then you have to use right hand grip rule to determine the magnetic field. So your right hand grip rule, make your thumb point towards yourself, and then you will realize it is anti-clockwise direction. So which is like this, anti-clockwise direction. Okay, another conductor, which is this conductor. This conductor is, let's say, here. Okay, draw a tangent at the position of the other wire. Okay, so that means the other wire is here. The other wire, let's say it is here. Then you have to draw a tangent. Okay, draw a tangent. So your tangent is this way. This is the tangent. Okay, now you have to use Fleming left hand rule to determine the force. Okay, so how to use Fleming left hand rule? First, you need to know the B is upwards. The B is upwards. So why it is upwards? Because your magnetic field is this way. At this point is upwards. You know, is anti-clockwise, right? So anti-clockwise. So at this point is upward. So that's why your B is upwards. Fleming left hand rule, your B is upwards. Your index finger is pointing upwards. And then second thing, the current, you refer to this conductor. It is a cross. That means the current is going in. So the current is going in. So we put it in this way. Current is going in. And after that, Fleming left hand rule, your force is to the left. Your force is to the left. So this way, the force is to the left. So at the end, this conductor will experience force to the other side. That is repulsion. Repulsion. Okay, so we use Fleming left-hand rule in this way. Okay, now let's say one more example. Okay, let's say cross and cross. Cross and cross. Okay, so the first cross, let's say I draw it here. So meaning that the current is going into the screen. Now you use right hand grip rule, make your thumb point towards the screen. Then the forefinger will twist in a way that is clockwise direction. Okay, so after that, another cross is just beside of it, and we draw a tangent. Okay, now you use Fleming left hand rule again. Your B have to go down. Okay, your B have to go down because the circular magnetic field here, when they reach here, it is downward. So your B have to go down, which is like this. Then your current have to go into the screen. So your current go into the screen, so which is this way, into the screen, 90 degree. Okay, then go into the screen because as you can see, this conductor is a cross. We use this conductor as reference. This conductor produce magnet. This conductor consider its current. This magnet, this one, current. And then based on Fleming left-hand rule, you will realize that the force is towards the left. So you have to use Fleming left-hand rule to determine. So it's to the left. So meaning that this conductor experiences force to the left. Okay, that is attraction. So that is how we understand it. Or if you don't want to use this way, just memorize it by heart. Opposite direction, repel. Same direction, attract. Then it is okay also. Now let's look at 9.8. Okay, 9.8, magnetic flux density. So this is the starting of formula together with calculation. So magnetic flux density, the symbol is B. It is also known as magnetic field strength. Magnetic flux density is magnetic field strength. Magnetic field strength. Okay, so when we say magnetic field strength, maybe you feel like, oh, electric field strength, gravitational field strength. So are they same or not? Actually, similar. They are similar. Their definition is also force per unit of something. Force per unit of something. Gravitational field strength, force per unit mass. Electric field strength, force per unit charge. Magnetic field strength, force per unit current. So it is also force, as you can see here, force per unit current, and so on. I have a lot of things there, but basically it's force divided by something. So divide by something. So force divided by mass, force divided by charge, and this is force divided by current. So relevant. Okay, now let's see the second point first. Magnetic flux density B, force acting per unit current on unit length of conductor placed at right angles to the magnetic field. So that means what? You have to look at this formula. Okay, you look at this formula. So what they say is, magnetic flux density is B, right? So if I rearrange this formula, Okay, I rearrange that formula. I will get B equal to F over I L sine theta. Okay, now we have to think of how to make the denominator to be 1. So current have to be 1 ampere, length have to be 1 meter. How to make sine theta to be 1? So it has to be sine 90 degree. Then it is 1. Okay, so everything is in 1 unit at the bottom. So in that situation, right, the magnetic flux density, the B, is equal to force per unit current per unit length at 90 degree. Okay, the conductor is at 90 degree. So which means how? Which means like this. Okay, you can see this again. The theta is 90 degree. The length is 1 meter. The length is 1 meter. And then the current that flow inside is 1 ampere. And then this conductor will experience a particular force. That force is magnetic flux density. So that is the idea of magnetic flux density. And of course, you can see another thing here, which is magnetic flux. Magnetic flux. Okay. Magnetic flux density, you already know, is how strong a magnet is. How strong. So that's why it's related to force. How strong a magnet is. But how about magnetic flux? So what they say is magnetic flux phi, this symbol is called phi, number of magnetic field lines passing normally to a given area. Okay, so unit is Weber. Unit is Weber. So the unit of magnetic flux is Weber, whereas the unit for magnetic flux density is Tesla. Okay, Tesla, capital T. Capital T, yeah. Okay, so different unit. So let's write down first. The unit is different. This is T. Sorry, this is Weber. Okay. Weber, and this is Tesla. Okay, they have different units. And what is the difference? Magnetic flux is actually what? Is the number of magnetic field lines passing normally to a given area. So let's say you have an area like this. You have an area like this. Okay. Then there are 3 magnetic field lines. Then that is magnetic flux. Magnetic flux is counting how many field lines. 3 field lines in an area of, let's say, 1 meter square. Then you will get the magnetic flux. How to get? Use formula. This is the formula. Phi magnetic flux equal to B times A. B times A. So the A must be area that is perpendicular. Perpendicular to the magnetic field. So perpendicular to the magnetic field. As you can see, magnetic field lines passing normally to a given field, to a given area, So that is the condition for area. So meaning that it is, let's say I put it in 3D. Yeah. So let's say this is the permanent magnet in 3D. This is north. Okay, now at the bottom we have the south. Okay, then we have the magnetic field lines. So let's say I just simply put 1, 2, 3, 4, okay, 4 lines. So 4 lines. Then according to the definition here, what they say is the magnetic field lines must be perpendicular to the area. So which area should we take? So of course it is the area that is perpendicular to this area then. So you take the number of lines in the given area, then you will get the magnetic flux. Of course, it means you have to use formula. No? We have to use this formula to get phi equal to BA. The A is this A. Okay, so let us label it first. The A is that A. So this is the A. And then the B you have to count. No? You have to count based on formula. Okay, the B. You take the B multiply with the A. B is the magnetic flux density, which is magnetic field strength. You take the B multiply with A, then you get the phi. So which is the magnetic flux. Magnetic flux is what? Is how many lines in a given area. Let's say, for example, 4 lines in this area. Okay, something like that. Now, next point. 1 Tesla. 1 Tesla is the units for B. So 1 Tesla is the magnetic field producing a force of 1 Newton per meter on a wire carrying current of 1 ampere normal to the field. Okay, so what are they trying to say? So they are trying to say B, okay, maybe we look at the formula. B equal to, okay, so right at the bottom here, B equal to F I L sine theta. Okay, so 1 Tesla equal to 1 Newton over 1 ampere times 1 meter times sine 90. Okay, imagine I have something like this. So if this is the situation, then we can understand how big is 1 Tesla. Okay, so of course you have to look at this to understand 1 Tesla. So it is 1 Newton per meter on a wire carrying current of 1 ampere. As you can see, 1 ampere. Normal to the field. Normal means 90 degrees. Then you will get the idea of 1 Tesla. Okay, now we move on. The magnitude of the force on a current carrying conductor. The formula is F equal to BIL sine theta. And find directions using Fleming left-hand rule. So we already discussed that. It's the interaction between the magnetic field and the current, which produce magnetic field as well. It's the interaction between the two magnetic field that produce the force. So if wire parallel to the field lines, theta equal to 0. Theta equal to 0. So theta equal to 0 means what? Means the wire is like this. It's like this. Okay. This is the wire, the conductor. So if the conductor is this way, it's in vertical, so it's parallel to the magnetic field, then your theta is 0. You put 0 into your formula, so you end up with force equal to 0 as well. If the wire is at right angle is like this, horizontal, theta equal to 90, and force acting on wire is maximum, and you can count the force by using BIL because sine 90 is equal to 1. So just use BIL straight away. Okay, so